All right. Excellent. We're back. For those of you on the stream, sorry we're a little late. Just so happens Chandler likes to have the most number of computers of all speakers. Keeping it quick, really excited to have Chandler Carruth back this year. It's awesome. He is the Clang lead for Google, LLVM in fact, there. And he also basically drives C++ at Google. And he's also on the ISO committee. So hey, Chandler.
All right, it's great to be back here. Everybody hopefully still awake, all pumped up after Michael's talk. Good, a little bit. Sorry if we had some delays getting started, but we're going to get started. So first, just a little bit of background. All right, I work at Google. I kind of lead our LLVM teams, part of our compiler group. I also am trying to kind of push C++ as a language forward at Google. I do a lot of work with the ISO committee, lots of other folks. I have the pleasure of working with Bjarne and Herb and everyone else on the ISO committee. But I'm here actually today to talk to you about something a little bit outside of my comfort zone, all right? So you have to bear with me. Because I'm actually, believe it or not, I'm actually a back-end guy. I'm actually an optimizer guy. It's a little strange. But I'm not going to talk about any of that all day today. Instead, I'm going to talk about C++'s dragons. Okay, now some people may be wondering, what on earth do you mean that C++ has dragons in it? Like, why the negative message, right? C++ is, it's a great language. Unfortunately, when we talk to our users, right, and for me, my users are all of the C++ developers at Google. And when I talk to them, what they tell me is that they feel more like this is how C++ is treating them. They feel a little bit immolated sometimes, all right? And I want to explain why they feel this way, because it's a little surprising, and how we can kind of make them more productive, make them happier, and able to use C++, really better, okay? The other thing I do want to clarify is that this talk is going to be a bit of a first for me. I don't usually do live demo. As you might imagine by the over-elaborate setup we have back here, this is going to be a live demo-filled talk, okay? And that may mean that everything will break, all right? We're gonna roll with it. We're gonna see what we can do, because my goal is I want you guys to actually understand how we're trying to develop C++ at Google, the workflow we want people to use at Google, okay? Before we dig into that, we need to understand why we're spending so much effort on a workflow and on C++, because we need to understand why C++ is hard for these developers. Why is it challenging for people to write C++ code? There are a lot of potential reasons. One reason that gets bandied about a lot is the history, the legacy from C. The way in which C++ has kind of evolved over the years has left it this way. And you actually see a lot of this in my previous talk from last year. I talked a lot about kind of the problems that mixing C++ and C can lead to. There are also problems due to kind of old C++. This is something that Bjarne likes to talk about. You can't evaluate C++ as a programming language based on code that is 10 years old, much less 20 years old. It was a different language then. Right? Trying to understand today's programming language based on code written 20 years ago doesn't actually give you the right understanding. There's also a certain other concept. I think of this as subtlety. I kept searching for the right word here. This is a quote from an interview that Bjarne gave where he indicated that, yes, C++ it's not only expert friendly, it may even verge on too expert friendly. Right? And that may be something we actually have to strike the right balance on, but it's the reality that C++ does afford itself of some subtleties. You can write subtle and very specific pieces of code in C++, and that's important. That's what makes it so broadly applicable, especially in native domains, in a context where performance matters so much. But I don't think any of these are the real problem. I think the real problem stems from one and only one thing, and that is complexity. Now, complexity is a really annoying thing to have be the root of your problem, because, as far as I'm concerned, complexity is both the solution to and cause of all of our problems. Every time we have a problem, right, we build a new system, we layer more abstractions, we pile the software stack higher, and it causes all of the complexity problems that we're also trying to solve. It's a very frustrating interaction. And I think complexity here is kind of an interesting problem for C++, because it has essentially nothing to do with C++. The complexity that is killing our programmers has nothing to do with C++. Instead, it has to do with the amount of code and the size of the systems, the software systems they are building. When we build large-scale software systems, we inherently suffer from the complexity of those systems. It's endemic. Rob Pike, someone who works at Google, you might be familiar with his name. He helped build the Unix kind of operating system, has a great quote where he says that the cost of complexity is exponential. He said this midway through a rant about complexity. And the real essence of his entire talk was that you can't keep building more and more complex systems to address the problems you have. You have to strive for simplicity. You have to decompose things and find simpler ways to do things. Because every time you add complexity, you add an exponential amount of cost. Because the complexity of your system is how it interacts with the other software subsystems, right? And so as you add your own complexity, you simultaneously interact with other subsystems and add complexity upon them. This builds and it grows and it compounds. It is absolutely just terrifying how much complexity we as programmers are asked to deal with in large software systems. The way we deal with it is through software engineering. And this is an excerpt from Wikipedia's kind of definition of software engineering. I'm not claiming this is the right definition or a good definition, but it's a pretty close approximation, right? The application of a systematic, disciplined, quantifiable approach to design, development, operation, and maintenance of software. I think this is a not bad summation of the activity of software engineering. And this is actually how we go about dealing with this complexity, right? Unfortunately, we sometimes get a bit carried away with the idea of engineering, and we think that it's more like this, that it's more like, it's fun and it's games and there are explosions and things flying and it's going to be awesome. It's going to be, it's going to be like a movie or something. Software engineering isn't particularly fun, but it is absolutely important. So when I say software engineering, I am actually talking about an activity, right? And here are some examples, because I want to make sure that we're all kind of on the same page with what activities do we consider software engineering, all right? This is things like factoring, right? Factoring the functionality in your application. Providing layers and boundaries to constrain the dependencies and the interactions which cause this compounding complexity growth. Building abstractions, all right? To kind of encapsulate the behavior, the functionality, and the subsystems. And the one that I actually really, really like is defining specifications, right? Defining some specification that you can actually support and maintain, and you can use to communicate with the other people and the other parts of the software system. And this is absolutely critical to what we're doing. Because simplicity is vastly better than complexity, all other things being equal. If we can get a simple software system to solve our problems, or at least a simple subsystem, a simple little area where we can live and solve problems, that is going to be much more rewarding, much more effective and productive than dealing with all the complexity. So our goal as software engineers, when we're going about this, we're trying to build abstractions with simple interfaces, right, to encapsulate complex functionality. And I think that this activity, this single activity, is probably the single most important thing any programmer does when working on large-scale software. But there's an unfortunate reality here, and that is that this takes an unbelievable amount of time, all right? And a lot of people, they get into this and they start getting misguided ideas because they're tired of the effort it takes to do this, and they start getting clever. I worry some days that they start thinking like Andre. And unfortunately, in these systems, this is not really a compliment. This isn't a good thing, okay? Because this clever brings more complexity, right? It brings more of these maintenance burdens. What we really want are simple solutions. And in order to get them from our engineers, we need to do something pretty straightforward. We need to give them time and energy to actually devote to these activities of engineering high-quality software. And that's going to be quite challenging because they have a bunch of other demands, right? They're trying to do a whole lot of other stuff, and let's face it, software engineers may not be the most, active individuals you've ever met, right? They may be a little bit on the lazy end of things. I'm the laziest software engineer I know. That's why I like making productivity tools so much. Otherwise, I would get nothing done. So we need some way of kind of, automating and accelerating, of improving the productivity of an engineer that is inclined to lay around and relax. And, so we need some tool to help you stay productive with these kind of, boring activities or activities that may consume more time than you would wish. All right? And that's really our goal in all of the rest of the stuff I'm going to talk about. But how do we get there? How do we automate and accelerate the manual tasks of writing software? Right? And how do we protect the programmers from feeling like they're getting burned? Every time they sit down to write code, they're getting burned by the complexity that they have to deal with. And that's where LLVM and Clang have come into play in a very large way at Google, and specifically technologies built on top of LLVM and Clang. Now, why did we seek out a new compiler toolchain to build tools for C++ programmers? Well, historically, GCC simply did not cut it. This is the simple fact. A long time ago, people tried to make GCC into something you could actually build complex, higher-order tools on top of. They tried repeatedly, and they did not succeed. It was a very grueling task. All right, they tried adding plugins. The people who worked on this were some of my colleagues. They worked very hard because GCC was a mature, functioning, well-tested, and well-understood compiler, and that is not something to be given up easily. We weren't able to make progress. We had to take a different approach, and so we ended up going with LLVM and Clang. And when I talked about this, over a year ago, I kind of related some of the experiences that we had with GCC, and specifically certain members of the GCC community, as about this productive. Okay, about as productive as filtering the ocean with the Brita pilcher to bottle it while wearing a Darth Vader costume. It doesn't get you anywhere, okay? Except onto my slides, apparently. But, despite all the Darth Vader references I'm going to make, it isn't fair, okay? It really isn't fair, because what I think people have missed is that this is largely a historical anecdote. This is not true today. GCC today is improving faster than I have ever seen it. It is a better compiler than it has ever been before, and the community working on GCC is one of the most amazing open source compiler communities I have ever seen. And we actually owe all of them a tremendous thanks for building the first and largest and highest quality open source C++ compiler that we ever had. And it's easy to lose sight of that. Now, they are working really hard, and they're actually headed in the exact direction that I think they should be headed in. They're modularizing their compiler. They're making the diagnostics better. They're making the user experience better. They are doing absolutely everything I think they should do. And in fact, the competition thing has actually worked. Clang has improved dramatically in the last year, directly as a consequence of the work going into GCC. And we owe that to the GCC community, and we have to remember that. The reason why we are still using LLVM is because LLVM is ready today, and GCC has not yet caught up on the modularity front and on the tooling front. All right? That's where LLVM is a little bit ahead, and unfortunately, we need the tools today. We actually needed them yesterday, and by yesterday, I mean 2 years ago. And so that's why we're really heavily invested in LLVM. It's mostly a historical and temporal accident. I think in 10 years, you're going to see a lot of modular, flexible compilers that can do very interesting things, lots of tooling. This isn't going to be a one-act thing. Okay, so that's that historical point clarified. Let's talk a little bit about LLVM, because I do work with LLVM. That's why I'm here. I'm going to talk to you about this project. It's an open source project. A lot of people don't realize that LLVM, first off, you may have heard it stands for something. It doesn't. It used to, like 10 years ago. It was a bad idea. They finally realized it and fixed it. It's just 4 random letters at this point, officially. But it's an open source project that really houses all kinds of compiler-related activities in the open source community, right? It has the core LLVM libraries, right, which make up kind of compiler infrastructure libraries, tools for building compilers and related tools. It also hosts the Clang compiler, which is a production quality C++ compiler. We have a linker that we're building. We have a debugger. It's a full C++ toolchain. It's the whole thing, okay? It really is the whole thing. And the first tool that we're going to build on top of LLVM is always going to be the compiler, okay? That's just a fact. You're going to start here. And it turns out the Clang and LVM, it's a pretty good compiler. I wanted to mention this because a lot of people don't realize. Clang and LVM is absolutely a production quality C++11 compiler. It's shipping on some major platforms in the world. You might have heard of one of them. It's called Apple. I know you might have heard of them though. We use it very heavily alongside GCC. This is a high-quality compiler, right? And it hits all of the important bullet points for a compiler. If you're looking at a compiler, you have some checkboxes, right? So the checkboxes go, you want to generate some high-quality code. You want to compile things reasonably quickly. You want to diagnose your broken code reasonably well. See my last talk for all the details on that. I'm not going to spend any time on this this time. And you want to get lots of important warnings, static analysis. You want to help the programmers out when they're actually compiling their code. Try and catch their bugs as early as you can. And this actually we're going to talk about a lot more. Before we get into all of the static analysis and bug finding things, I want to talk more about tools. And specifically, I want to spend the first section of this talk talking about authorship and modification tools. Okay? This is not tools for other stuff. This is authorship and modification tools. And to start this off, I have to tell a bit of a story. This isn't quite as good as Herb's story about an Atari. So when I was very, very young, I mean this kind of young, I was given a pretty classic toy. I liked puzzles, and so my parents got me a puzzle. It's one of the puzzles where it's a board with differently shaped holes and pegs, and you have to find the right peg to fit into the board. It made sense for my somewhat analytical mind, even at that age, right? I really enjoyed it. My parents were a little bit concerned, however, because they turned around one day and found that I had climbed the shelves under my father's tool rack, gotten a tool off of the rack, gotten back to my puzzle, and systematically driven the square peg into the round hole. This may have been, telling about the rest of my life. But this is exactly what we actually find ourselves wanting to do with C++ code time and time again. We have a square peg, we have a round hole, and we have absolutely no choice but to put the square peg through the round hole. And usually, we're just kind of out of luck when we get there. But if we have tools, right, if we have a really big hammer, sometimes with some shrapnel, we can actually make this look the way we want it to look. And this is essentially the essence of refactoring C++ code. So we set out to build Fowler's catalog of refactoring tools. We're just gonna like IDEs have been doing this forever, right? Like there's a long history of how you refactor code. We know how to do this. We'll set out and do this. And we built a bunch of tools. We built a renaming tool, an inline extract, all these fun tools, and absolutely none of them worked, which is a bit surprising to us. I mean, they worked, right? There were prototypes. They weren't actual functioning tools. They could do the transformations we wanted. But those transformations weren't interesting to programmers because after you did these transformations, you got some code that looked approximately like this. And this is not the kind of high quality, like nice, beautiful C++ code that you want to come out of your automated tool. Because what we've done here is we've inlined a method call which produces this magic widget object. Unfortunately, that method call had a local variable and had a function call, so we had to create a scope for it and then insert it, and it was indented poorly, right? But then we were able to create the variable and thread the variable through, but then we renamed the function that we're calling as well to bar, and so the indent's all wrong there. I mean, none of this code makes any sense at all. And if you actually do this on any kind of scale, right? Remember, I'm talking about large-scale software systems. If you do this 10,000 times, you are going to be very sad about your next job. Because what you have done is you have taken the hard problem of refactoring a lot of code, which is a problem that scales, linearly with the amount of code you have, and you replaced it with another hard problem of reformatting all of this code, which also scales linearly with the amount of code you have. And so you've not really addressed the fundamental problem here. You're still in a situation where at some point you run out of time, you cannot actually deploy these changes, you cannot use these tools. The tools just don't work the way we built them. Okay, so at this point we had to take a big step back. Right? We had to really reconsider exactly how we were designing and building these tools. We asked ourselves, what was the absolute most important tool to reduce wasted time? You won't be surprised by the answer. It was very much informed by the previous slide, right? Formatting white space. Yes, this stuff. it may seem a bit odd that this is what we decided to spend, lots of engineering time to solve, but this was actually important, okay? Because your code is just, it's a unique and beautiful snowflake. And so some people don't care about formatting, bless you. For the rest of us, our code is a unique and beautiful snowflake, and we really, really care exactly how, and we've crafted it to be perfect. We've gotten it right, okay? Until we start a code review. And the code reviewer, unfortunately, believes that it is the wrong unique and beautiful snowflake, and they would like it to look like their own unique and beautiful snowflake. And what proceeds is an utterly useless argument between two people who are utterly convinced that they're both right, and they're not listening to the other person. Can you imagine how much time we were wasting? You probably can, because you probably wasted this time yourself, arguing over which side of the white space the asterisk belongs. Because that matters, right? Well, unfortunately, it does matter. It does matter because our challenge in C++, again, is not C++, it's complexity. One of the ways that human beings deal with complexity is through patterns, right? Patterns that we can recognize, learn, internalize, and understand very, very rapidly. When you format your code well, right, when it actually is laid out in a consistent being the most important, a consistent, logical, clear way that separates the different concerns, emphasizes the things which need to be emphasized, hides the parts that are completely irrelevant, it is tremendously simpler to read it and to understand it, especially as the amount of code you're reading grows, especially as the complexity of the code you're reading grows. I actually think of this a lot like Go. I don't know if how many folks here have played Go? Awesome. So how many folks here are good at playing Go? By the way, my hand is up as a demonstration. I'm terrible at playing Go, okay? So if you've ever talked to someone who's good at playing Go, they may have tried to explain that you don't actually sit here and look at all of the billions and billions of permutations on the board. That's a waste of your time. You can't do that. Instead, you have to learn and understand that there are different patterns and shapes, formations and structures on the board which will tell you what is happening, which will give you a very clear idea of how to proceed, what the risks are, what the trade-offs are at this point in the game. That is exactly how human beings read C++ code and every other programming language, right? And so this is no different. Unfortunately, formatting does matter. It matters more than we would like it to matter. And a lot of people responded immediately to this theory with like, yes, but indenting's easy. Emacs has been indenting my code forever. Visual Studio has been indenting your code even better than Emacs forever. This is not a hard problem to solve. We've solved this already. But indenting really is easy, and it's really not the problem. Formatting is hard because where do you break the line? All right, where do you break the line? This seems like such a simple question. We've spent several person years trying to answer this question for C++. It turns out to be stunningly hard. But enough with all the slides. The only way I'm going to have a hope of explaining this is to show you. If we can get to the demo. Excellent. All right, so remember, folks, this is live demo. Please be gentle and kind. All right, so I have a little live demo here for formatting C++ code. Now, I'm going to use my personal editor of choice, right, which is Vim. By the way, we are serious about integrating this support into as many editors as is humanly possible. All right, if you choose to use Emacs, that is fine. I mean, you're wrong, but it's fine. I'm okay with that. It's a choice, right? Anyways. So I'm going to use Vim, but it really doesn't matter. So this is some code. It's not very good code. I'll actually admit that. It seems kind of silly, somewhat contrived, but it's at least well formatted, right? It flows cleanly. It seems like a reasonable thing to have here. But we may want to actually change a piece of this code. Let's say we actually are renaming the method with, the poor man's refactoring here, right? We're going to take some method. We're going to rename it some really, really long method, right? Seems like a reasonable thing to do. But now, you have a formatting problem. At least if you like narrow width code, you have a formatting problem. If you have some column limit, you may have a formatting problem. I'm a true believer in the 80 column limit. How many folks here agree with the 80 column limit? All right, good. I have a good audience. For those who don't agree with the 80 column limit, you are again wrong, but that's okay. It's really okay. The interesting thing about column limits is this. I think that column limits are almost inevitable, not because they're actually a good idea, but again because we're human, right? How do we read things? Talk to any newspaper editor, right? Anyone who's worked in print, and they'll tell you that human beings read narrow columns of text faster. I don't know why. I have no idea. But it seems reasonable to want to have some column limits. For the sake of the presentation, 80 happens to work really beautifully on the projector, and so I'm going to stick with 80. It's also right. But at this point, we have a problem, because if I go to the last line of this column, if I try to go to the last line of this column, you're going to see that it's 88 columns. It's not going to work very well. Fortunately for me, I can mash a button. And Clang format, which is actually integrated in here, you can see that there's a Python script. You can see it at the bottom here. It's a little Python script. This is live, right? That's actually doing this for me. And so it's automatically going to figure out what the best place to break the line is in order to keep it to 80 columns, but keep it as dense as it can. Okay, that one's actually pretty easy, though. Emacs and Vim, they'll do this one just about as well. But you might need to do something a little bit more interesting. So let's say we come in here and we want to change the names of these variables. We're going to make this one kind of long. This one's also going to get a lot longer. I'm sorry for the contrived examples, but when you're doing formatting, all of your examples are contrived. And when we format it again, it's going to keep wrapping around that column, right? It's not forming new lines. I didn't have to go and find the new breakpoint, delete the old one, right? Stitch the lines back together and hit enter 3 times. I hate doing that. I don't know, do you guys, like, this to me changes the way I write code, because now I just type and I mash a button and it fixes everything for me. And it doesn't even matter how complex I make this, right? So I'm going to make this as complex as I can realistically. So, my long namespace. Again, I'm trying to make this look bad. I don't expect real code to be quite this bad. But now, this is getting kind of crazy. But when I mash the button, it fixes it for me, right? And I can keep going here, right? I can delete some of these characters. I can go back. And that's fine. It doesn't care. So I can keep editing all this stuff down, and it's just going to fix it for me just by mashing a button. It's going to keep reflowing the text. And you'll note that it's doing something kind of clever here, right? It knows that this const, right, that const needs to be attached to that closing parenthesis for clarity. If we just sink a const down into the middle of your function, you're going to read that the wrong way every time. And so it's sacrificing placing the F after the E. It would fit, but it's going to sacrifice that to try and pack that const in the open curly more closely, right? This is actually a really complex thing. The thing that blew me away was when we started doing this, it turns out that this is essentially tech, but for code. We actually build the text style penalty set for every potential line break in the range of code. And then we use Dijkstra's algorithm to navigate the path and find the lowest penalty set of line breaks to lay out a region of code. It's really amazing. It ends up being both complex and also kind of elegant when you end up with it. And that's been really satisfying. But the problem is that this just isn't ugly enough. A human being has some chance of making this work. We need to get to the point where a human being would just give up and go home. So if I channel Andre for a little bit here. By the way, Andre, I may get this wrong because I don't actually know how templates work. It's true. You can destroy me later, though. No. Here we go. Something like that, right? So now that's really bad, okay? I mean, that's really bad. And sadly, we're not done yet because that's just half of the bad that we have to suffer through here, right? We now have to go and collect all of this code here, and we have to duplicate it. And this is going to get just all kinds of ugly at this point, right? I don't even know what I'm doing here. So at this point, right, I just mash a button and it makes it go away. All right, and this is just amazing, and it will keep doing this. In fact, this isn't impressive enough. We need to do something more hard. So let's bail out of this one. Let's try something a little bit more fun. What if you have macros? the bane of every editor and code analysis tool's existence. Half of this code isn't compiled half of the time. That's going to put a wrinkle in this, right? Like, what happens when we say, actually, no, this is the wrong name. This needs to be a foobar baz builder, right? Well, as it turns out, I'm just going to mash a button and it's going to format both sides at the same. Is that too fast? Hold on. Both sides. So what it's doing, it's actually going through and it sees you've got a branch in the preprocessor. It's lexing this thing. It's not parsing it. The shocking thing here is that this is not a parser. We don't read your headers. Okay? Because it has to be fast. This has to be something you can have in your editor that you're using constantly, almost every keystroke. So it's just a lexer. It's scanning, it recognizes preprocessor branching, it tracks each side of the branch, and once it finishes the branch, it weights all of those independently and aligns them independently. And this works pretty well. You can break it if you have, a grouping operator with only half of it inside and half of it outside. We lose track of that. But it actually does a pretty good job of actually helping you actually manage even complex system code. I mean, so we've got this example, but there's one that's even better in my opinion. So this one's one of my favorite examples. Oh, no. So this is code that actually looks very much like a bunch of code in Clang and LVM. We have some enum, right? Something, and we're doing a switch, and we've got some code. This is not actually a small piece of code. This is actually a huge piece of code that we're replicating, 50 or 100 times inside of a macro. We want to be able to format all of this code, right? It's really beautiful right now, but if I decide that like I don't actually need this condition, maybe I know that I don't need it, and delete that, now I have a problem. And you'll note that I'm highlighting a whole range of lines here. I don't know if you can see that, but I'm highlighting the whole range of lines all the way up to the top. And then I mash the button and it's going to reformat all of that, right? I can select any grouping I want and it'll actually move all of that over. And it didn't disturb the macro. It understands that a macro definition doesn't actually interact with the stuff around it, unlike a preprocessor selection. And so it understands all of that. And then the thing that just absolutely blew me away was when I wanted to come in and I wanted to say, like, actually, this should be a static assert. Now I've got like the backslashes all wrong, and it fixes it for me. So it will actually reflow code within a macro definition. As it expands lines, it'll trail those backslashes down the right-hand column, right? It keeps all of it lined up for you. I love this tool. Okay, so that's formatting. Now, this may seem like a trivial thing. We can go back to the slides now. This may seem like a trivial thing, but this saves our programmers so much time. Yes?
I just want to make a comment. This is a big thing in publishing, too, because when you're trying to write and you don't know whether people are going to be consuming on electronic or on paper,
yes.
On electronic, you don't know whether it's portrait or landscape, you don't know what the font size or anything else. The single biggest problem that I and many other authors have been wrestling with is how do you write when you don't know what the output device is and you still want it to look good?
Yes, so Scott sums up that this is actually a problem in publishing code, I assume, in written material. In publishing code and written material, you have to prepare code and then reformat it in different ways on the different mediums, on the different devices, on all the different ways people are consuming it. It's absolutely true. We haven't actually spent a lot of time working on that. We've actually just been kind of laser focused on getting the developers empowered. But it's an obvious application. And all of this is built in a library way so that you can embed this into anything you wanted. Literally, you can embed this into anything you wanted. Okay, so that's Clang format. That has been a work of over a year's time, right, to essentially remove the most annoying and least useful and most time-consuming thing we saw our programmers doing. And it has been wildly successful. I think it is actually my single favorite tool. And so now, I'm going to tell you about another tool to save you some time. And while this tool, I think, is actually a little less impactful today, I think that over the next 5 years, this tool is going to turn into something even more powerful. We're calling it Clang Modernize. So we're going to try it out if we can go back to the demo laptop. All right, so we're just going right back into demo because I don't like slides. I like demo better, as long as it works. All right, so now we've got some modernization stuff. Now this is going to be a little bit more awkward to demo because you have to understand Clang Modernize is one of the first real refactoring tools we've started to build on top of Clang now that we have all of the infrastructure in place. Right now that all of the infrastructure, including formatting, is in place, Clang Modernize is going to be one of our first and premier tools, okay? And as such, it's designed to edit your code. All right, and so what I have here is I have a bunch of before and after files, right? And I have a little script which I will run, which just resets everything to the before state. And I'm going to refactor the after side, and we can look at them and try and understand exactly what's happening. So first, let's look at null putter. This is my favorite modernization, because today in code we have terrible code like this with a 0 for a null pointer. And I don't like zeros for null pointers. I don't like things for null pointers. We've had too many bugs with this. So if I go get into the tree here. So at this point, we're going to run clang modernize, and we're going to, I want you to be able to see what it's doing, so I'm going to ask for it to print out a summary of the changes it's making to your code. And let's actually ask for specific formatting. Let's say that the formatting style is LVMs, because I'm an LVM hacker, and so let's use LVM style. And now we're just going to look at the null putter on the after side. This is going to run. It's going to say, like, hey, we found a use of null pointer, and when we look at this code, it's replaced 0 with null pointer, right? Great, cool. We've built a tool that's just as good as sed. It's awesome, right? Okay. So we need a little bit better example. Hold on. I can do better. I promise I can do better. Okay, so what if we do something a little bit more exciting? Yeah, what about this one? So imagine you have, a lovely type hierarchy, right? You have a base class and a derived class, and you're worried about actually misaligning the overloads of your derived members and them not actually overriding the base ones. Well, C++11 we got a great language feature to actually help you track this down. We got the override keyword, right? And clang modernize can help with this too. So let's see. We can just go over and take a look at this. So we run at this, it's going to say, like, hey, we found 2 places to add override. And if we look at the code, you're going to see that's added the override keyword in 2 places, right? Pretty straightforward. But it's actually, the interesting thing here is it's not going to blindly add the override keyword. It's going and it's looking at every single virtual interface here, and it's finding exactly the methods which do in fact override those on the base class and adding the override keyword. And now you can go through and look at all of the methods which don't. Right? And you can find every single method which does not get one of these keywords and ask why. Maybe that's a bug. Maybe there's a problem there. And you can start to actually clamp down on exactly how your derivation is working. Yes, Andre?
Is there a finalized?
Patches welcome? Not yet. That's a great idea, though. We should do that. Yes?
Can you ask it to tell you the places where it didn't put the override?
That's a great question. At one point we were talking about this, and we were actually saying that we were going to have it warn when it found something with the same name but a different overload. I don't know that we actually implemented that, but since it's a live demo. No, we haven't implemented that one. I'm sorry. So our idea had been that we'd actually have this tool warn you as you go, and so it would add the override when it could, and when you had a name collision, right, but a different signature, we could actually produce a little message saying, by the way, we skipped these methods because they were weird. And then you can go investigate them. All right. So, can you speak up? So I ran the undo script. Note that it said it only placed 1 override in there. I could even look at it. See, it has the float, and it didn't add override. My undo script synchronizes the before and after, right? Because it edits the code in place, and I wanted to be able to do this. All right, so let's look at a few more things, because this is actually, this tool actually has a lot of more interesting stuff. So we've done null pointer, which is kind of trivial. Override, it's interesting, but it's not really a huge change. But let's look at one. Let's look at auto. This one I found really interesting, and so this one kind of goes to that almost always auto rule that Herb talks about, right? Because we shouldn't be writing the type name here twice. It's kind of redundant. We know exactly what type this is going to be, like 5 characters to the right. We don't need to write it here, and the tool will actually go in and it'll do the kind of obvious thing of saying, like, well, we can put auto in there, right? And if we look at it, you're going to see it said, like, no, it's auto X in US, right? And you can do this with all kinds of things. I think we handle new, and I think we handle when you assign to an explicit temporary constructor, just like in your post. But I haven't checked that. So we might need some patches there. But that's the idea of this is to add the autos that are unambiguously better, right? There's no ambiguity whether this is like a better representation. Okay. So let's do something even more interesting. So you guys remember autoputter, right? You remember autoputter. So unfortunately, we have a problem where there's some interfaces and some code bases where autoputter is actually, it's widespread, and it's in the interfaces, it's everywhere. And most frustratingly, there exist cases where autoputter is not equivalent to unique putter. And finding those cases is challenging. Leaving those cases alone is very challenging. So what we have is a tool that will go through and it will actually analyze your use of autoputter, and it will give you a nice modernized user interface using unique putter. Now, it'll even fix up the pound includes if you have the wrong one. All right, so this was a really, really great feature. Just goes through, unilaterally fixes all the places. It's great. Happy so far? All right, we got a couple more. My favorite one's still coming. All right, so let's see if we can do something even more advanced than this. So we've done that. Let's try range-based for loops. Well, I got the wrong file here. There we go. So we have kind of your expected, somewhat terrible for loop, right? C++ 98 code is littered with this stuff. I mean, littered with this stuff, and it's horrible. And I can't even read this anymore. Having worked in C++ 11 for about 2 days, I stopped being able to read this code. For my own sanity, right? And the best part is that now I don't have to. Whenever I see this code, I simply come in and I'm like, no, I'm not reading that code. I am going to fix that code. And then I never look at it again, because now it looks like this. And this transformation is where things get really interesting, because this does something wholly different from all the other transformations. Like, I've given you a little example here, but there are subtleties here from like all corners of the place, right? What's the difference between cbegin and begin? What's the constness? How do you pick the const and referenceness of the auto variable for your loop body, right? How do you name the variable in the loop body? We didn't have a number variable in the previous loop, right? Like think about this for a minute. There's no number variable here. We're actually parsing the name of the container, recognizing plurality, stripping it off to form a singular name, which is probably a good name for the element. We'll also look at your iterator name. We have a bunch of generic choices, right? We actually have heuristics to try and make this work. And once you do this, you'll realize something really special. This didn't just take horrible, ugly, unmaintainable code that I don't want to stare at and turn it into beautiful code that says exactly what I meant. It also made this loop faster. This is a performance win. On every compiler I know of, range-based for loops run faster. I can explain why. Look at my comparison. Look at this comparison here. That end call. This end call is the bane of the optimizer, because about 10% of the time to 1% of the time, usually the 1% that matters, this function is big and that container is complex. And you call end on it in the loop condition. And the compiler says, you know what? I'm out of smarts. I've run out of everything I can do. I have no idea what that function call does. And it calls end on every single iteration of the loop. Doesn't matter what you put in the loop body, right? This will happen in the optimizer. But you know what won't happen in the optimizer? It won't care about this. It will call end once, it will call begin once, and then it will iterate over a fixed range. This can actually take loops from runtime loops and turn them into compile time constants. Okay? I actually have found several cases where that happened. The compiler said, oh, you're not mutating the size of the loop, the size of the container? Oh, okay, I can compute the answer. Here it is. It's 42. That's the kind of optimization I like, okay? So this one is my personal favorite transformation we have. However, I think that I have one that Sean might like even more. And so now we get to a really clever transformation. No, I'm in the wrong one. I told you it was live. Okay, so this is pretty standard C++ 98 code. Everyone wrote this. Literally everyone wrote this code. And they didn't write it once. They wrote it thousands and thousands of times all over their code base. Everything looks like this. And this is not very efficient, right? Here we have exactly what Sean was talking about, where we are actually syncing the value of name through this interface and into a member variable. And there's a significant cost here, right? There's potentially an allocation. For a lot of people who have thread-safe allocators, there's a synchronization event and an allocation every single time you construct one of these objects. And there's no need for that at all. Fortunately, we can modernize it. And so with a little run of our tool, we get code that looks like this. All right? Yes, Scott.
Why did you decide to go that way rather than doing forwarding?
I have no idea. I didn't write this particular tool. So the question was, why did we decide to go the route of a by value parameter and std move rather than forwarding? And I actually don't know the answer to that. I didn't write this particular tool. And that's a great segue, thank you, to the other thing I wanted to say about this tool. The tool I just demoed here, this modernized thing, I want to give a very specific shout out. This was the first really amazing tool that some folks outside of Google came into the LLVM community to help build. A bunch of folks at Intel, Edwin Bain and some other folks at Intel, just did an amazing job building this tool. And they deserve all of the credit here. They've been working on this for a lot of months, and they've built all of this functionality, and they're still just kind of ramping up. I think that this tool is going to cover an amazing range of modernizations, and the best part is, if there's a better way to rewrite this, we can detect that, and we can add a rule for that, and then we can find the better ways to rewrite it. We can kind of encode a lot of these patterns that you've seen throughout the entire talk here at GoingNative. Okay, so with that, I think I'm done with this round of demoing, so we can go back to the slides. You can see that I was prepared for my demo to work in the expected way. But now for something completely and utterly different. We've talked a lot about authorship and maintenance tools. I could keep talking about authorship and maintenance tools for a very long time. We have a bunch of other tools in the pipeline. We're really excited about a lot of them. But I wanted to switch gears just a little bit here and talk to you about something different. I wanted to talk about a different kind of tool. Tools for debugging and protecting your code. Now when I say protecting your code, I mean protecting your code from bugs. How do we keep bugs out of our code? How do we get the bugs we have out of our code? How do we even discover the bugs that we know are there, but we don't even know how to track down? And fundamentally, how do we prevent this? Right? Because this is what we don't want. And so we need ways to actually protect our code. And I'm going to talk a little bit about a different suite of tools targeting this use case. So we use two primary things at Google: static and dynamic analysis. Tools, static and dynamic analysis are not new tools for this problem, but I think we're using them in some interesting and novel ways. I'm going to try and talk a little bit about the highlight reel, essentially. So we have this fundamental theory. It's an 80-20 rule, but in a different application. We want 80% of your debugging, right? 80% of your debugging should happen statically, as close to the compile time, preferably during your compile, as possible. 80% of all of the bugs you have to track down should be caught by the compiler. And these should be caught with warnings, static analysis-based warnings that have a very low, near zero false positive rate. Not zero, right? We're okay with forcing you to rewrite ugly, strange constructs to kind of idiomatic constructs to make it clear that there's not a bug there. But we really, really want to keep the false positive low. We want everyone to be happy with every change they have to make to their code because of one of these warnings. Then we want to go after this long tail of really nasty, really subtle bugs that consume, probably 20% or more of your time debugging, right, with zero false positive dynamic analysis tools. All right, and zero false positive is a really hard goal to set for yourself. But we're serious about it. We really want this to be so close to zero false positives that there's never a question. When one of these tools says you have a bug, and you start fixing it. You don't have to debate whether or not this is a real bug or not. All right. I'm going to talk about static analysis first. And there are kind of three components to how we want to do static analysis on top of Clang and LLVM. The first one is nothing new. They're compiler warnings. We've been over compiler warnings. I talked about them at length in my last talk. I'm not going to go back over all of the compiler warnings. One thing I do want to remind you, though, these aren't just warnings to catch kind of typo bugs and casual errors. We're thinking of compiler warnings around model checking static analysis, right? Where you define some restricted, narrow model of programming with a particular interface. One that we can check very aggressively in the compiler very quickly and do it on every single compilation. Once you opt into one of these models, right, we can provide very high quality static analysis results on every single compile. Last year I gave an example of thread safety model checking, and specifically synchronization-based model checking, and it's an area where we think that this really applies well. We want to grow the support for different models in that domain and in similar related domains. The second component of static analysis is an offline static analyzer, a traditional offline static analyzer that actually goes and does much more computationally expensive static analysis to try and find bugs that are very, very unlikely or maybe even never happen in real uses of the code today. They may be totally latent bugs, but which are there and to help you, find a way to write a test for it, fix it, and actually improve the quality of the code. And I think I want to go ahead and demo the static analyzer next. If we can go back to the demo laptop. This was going to be the shortest demo. I don't have a lot of demo for this one. All right, so I have some somewhat terrible code here, which I actually kind of apologize for. This is horrible code. I'm not endorsing this code in any way, right? But it illustrates the point, okay? So this is code that is opening some file object and closing it. At least it's trying to. And there's the open is actually modeled as a heap allocation for some strange reason, not claiming this is a good idea. But we need a way to actually analyze this because there's this latent bug here. By the way, raise a hand if you think you've spotted the bug. Anyone? Got a few hands. Not too many hands going up, though. So this is kind of a surprising bug. And I'm going to do this weird split screen so that you can see it better. Because otherwise, it's a little bit hard to see. So if we run clang and tell it to analyze this file, and we're going to need to give it the file name. So, right, it's going to say, like, you called an object pointer on a null thing, maybe. But this is useless, OK? The problem here is that I have absolutely no idea why this bug occurs. Anyone figured out the bug yet now? Few more hands, still not too many hands. This doesn't really help programmers. What we need is a way to kind of explain what's actually going on here. And fortunately, Clang provides a really, really nice way to do that. So see if I get the command right. OK, so this is the more rich output. And I'm going to scroll up. We're going to kind of step through this as best I can here. All right. So it's going to start off by saying you've called a C++ object pointer. You called a method on a C++ object, which is potentially null. And then it begins its logic trace. OK? And so it starts off that you assume that f, this first f, is not null, okay? And that means that we're going to take the true branch through that if. We're going to then hit the next branch. This one is going to simply, take the true branch. It also considered the false branch, but it's just explaining one path through the source code which leads to the bug, right? Then we're going to say, like, here we've assigned a new value to f under this branch. Then we assume that f is null. And we know to assume that f is null because we've tested that f might be null. It actually derives the set of possible states by actually looking at the control flow you yourself has written and the other code around the control flow that you yourself have written. Okay? Then it says, like, okay, so if we assume that f is null the second time we assign to it, then we take the false branch and we fall down to line 19 where we call close on f. Now how many people see the bug? This is why static analysis matters, right? Nearly every hand in the room went up after we displayed this lovely message. That is so much less time than standing and staring at this code forever. Yes, we have another bug in the code. Yes, there would be many bugs if there were exceptions thrown here. This is a very, very simplified example, and it's actually taken from a code base that doesn't use exceptions and is not exception safe. Remember, I started off by saying I'm not endorsing this code. OK. So that's how the static analyzer works. We can hop back to the slides now. So the final component of static tooling that we're building is offline inference. All right, and this is essentially taking all of the power of the static analyzer to kind of explore the permutation of possibilities based on the code structure you've written and feed it into a tool much like Clang Modernize, right? A tool which can then go through your source code and rewrite your source code with annotations corresponding to particular models. Models that the first component of static analysis can check at compile time. And this closes the quality loop for how you debug your software statically, right? Every time you build, every model you've annotated in your code is checked quickly at compile time, and you get immediate feedback from those bugs. After you build, the static analyzer can give you, more rich results. It can explore the possibilities. It can help you realize what is and isn't tested, what is and isn't asserted and documented properly, the invariants that your code has, but aren't actually manifest in the code. They're just in your head still. And then, as the third stage, you can bring that entirely all the way back around and annotate your code with that added information so that you get the next round of reports much faster, and this accelerates the entire development process. So that's how we're designing kind of the static checking of source code. Okay, unfortunately, the inference tool isn't here yet. It turns out that static analysis for C++ in Clang is actually still really, really new. I'm always surprised by this. It's much less mature than a lot of the other parts of the system. And so it's something that still needs a lot of work. We still have a lot of work to do here, but I'm actually pretty excited about it. Having this kind of closed loop cycle for how to check your code increasingly quickly and increasingly strictly over time with very low effort and engagement from the programmer is a really powerful model for maintaining and debugging code. Okay, so what about those really bad bugs, right? The ones that we aren't going to catch statically. What about the bugs that do this? We haven't really dealt with those yet. Those are not the bugs that you catch with static tools. Remember, 80-20. 80% are the easy bugs. You would have caught those anyways in your testing. You would have found most of those bugs. None of these are going to be revelatory bugs for you. What they are going to be is diagnosed rapidly. Right? You're going to spend a lot less time on those bugs. And all of this is about automating and accelerating your time so that you can spend that time thinking about software more, engineering the software better, crafting it better, and forming higher quality software. So dynamic analysis is not a new system for doing these types of bug checking. There's Valgrind, which is kind of a widely known Linux tool. There's also Pin, which is, I think, an Intel tool. I don't know much about this one. And there are a lot of other tools here, okay? This is not news, okay? But there are also problems with these tools. They haven't caught on. No one's using them. It's really rare for me to go to a group or a team and say, like, okay, when was the last time you ran all of your tests, all of your integration tests, all of your smoke tests for your release, all of your canaries against production traffic? When was the last time you ran that under Valgrind? And they look at me and say, what's Valgrind? And that's not really the right answer, right? It's not reassuring. And there are some reasons for this, right? Maybe they're just too slow, and Valgrind in particular is notoriously slow. We're talking 10 and 20x slowdowns to your program when you run it under Valgrind. They also miss a lot of the bugs that you really want to catch. For example, Valgrind, if you're not familiar, Valgrind is primarily a memory safety tool, and yet Valgrind misses most stack memory bugs, like stack overflows and underflows, and the things that lead to security problems, right? This is a really bad weakness for your dynamic analysis tool to have. The other problem they have is they don't really help you fix the bug, because these dynamic tools are working on the concept of binary instrumentation. You hand them your program, right? And they kind of instrument the actual program. The actual binary you give them, they run it in a special environment. Maybe they JIT it, maybe they run it in a VM. There are lots of strategies, but it's all based around this binary. By the time you have a binary, you have thrown away all of the information about the source code that would help you understand it. It's kind of like that first message from the static analyzer, which I printed and no one had a clue what the bug was, right? That doesn't actually accelerate anything, it just confuses users. And so all of these things kind of conspire to make these tools less attractive. This is where a new group of tools called the LVM sanitizers come into the picture. Now, this is also not a new idea, right? This is not, there have been compiler instrumentation-based dynamic analysis tools for many years. However, no one has really done the engineering work and the kind of, the grungy integration work to really produce a production quality set of dynamic analysis tools based on compiler instrumentation to really get them to be high performance, to get all of the features that we want out of them. And that's what we're trying to do with the sanitizers. So the number of the sanitizers is 3. First, we have address sanitizer. This one sanitizes your addressing, how you index into things, how you compute pointers, what you do with the pointers, where you store them, all those types of things. The next one is thread sanitizer. This one is a data race detection tool, all right? It's going to find places where you have threads that race on data values, right? Considered the hardest bug to track down, especially on x86, which hides it almost always, right? And then we have memory sanitizer. And this one is the newest of the 3, and it's trying to sanitize uninitialized memory, reading uninitialized, unpredictable data out of memory, and then depending on that data in some way. Now, all 3 of these are based on a technology called shadow memory, okay? The idea of shadow memory is essentially that you partition your virtual address space, and you map a huge section of it, sometimes half of your virtual address space, but you don't actually use all of it. The reason you have this partitioning structure is so that for every address in the program, every valid address in the program, you can map that address trivially into some address in your shadow memory. And this allows you to essentially associate metadata about every single address in the running program without really any overhead other than the overhead of that piece of metadata, right? And so if all you're doing is tracking a bit, you get 1 bit per bit of your address. Right? And that's a really, really phenomenal thing to be able to do. And when you factor in things like alignment and other factors in C++, it turns out you can get the overhead well below 1-for-1, bit-for-bit mappings. And this means that you can do some really fascinating analysis, dynamic analysis, of exactly how these addresses, how these pointers are moving through the program. Actually, I lied, there are 4 sanitizers. However, the 4th one's weird, okay? The 4th one's totally separate. It's also my favorite. The 4th one is, we call it undefined behavior sanitizer. It's a bit of a misnomer. All 4 of these things find strictly undefined behavior in C++ code. But the 4th one is kind of the grab bag where we placed all of the language semantic-based undefined behavior analyses, right? Everywhere in the language it says, if you do this, the behavior's undefined. What we do is we actually instrument first to see if you're going to do that. And if so, we report an error, right? Rather than actually directly entering undefined behavior. And this allows us to actually catch the overwhelming majority of undefined behavior in C++. It's not complete. There are definitely some holes here. But if you actually take all 4 of these together, what you end up with is with one of the tools having a high probability of catching any particular piece of undefined behavior in the language standard, except for 2 or 3 that we know we can't check right now. Okay? Now, one thing before we go any further, I have to reiterate this. I feel like people actually lose sight of this a lot. Dynamic analysis does not work if you do not test your code, because the analysis you are performing is on your code, and it has to run somewhere, somehow. If you do not write good unit tests that exercise the edge cases of your code, if you don't write integration tests that check how your code interacts with other people's code, if you don't write system tests that actually bring up a realistic system under this instrumentation, and if you do not take your production code and run it under a simulation of production traffic in a canary mode, if you don't do these types of testing, you're going to miss categories of bugs, because these tools only help if you're testing. Now, I actually kind of like this. It's a good incentive, right? Because this way, we know that you need to write tests, right? You already needed to write tests before we said this. But now, when you write your tests, the value proposition of those tests is going to be orders of magnitude higher. Make sense? Okay. So now I'm going to go back into live demo. If I can log back in. All right, so now we're going to try and demo, or I'm going to try and demo these dynamic analyzers. Okay, so the first one I'm going to demo is address sanitizer, and I'm going to spend probably the most time with address sanitizer. It's the most mature. It's also probably the single most valuable And I say valuable, not the best, most important, or my favorite, but you cannot underestimate the value of this, because Address Sanitizer, time and time again, is the tool which finds security vulnerabilities. Sometime take a look at the fixed security vulnerability list in Safari, WebKit, and Chrome, and Firefox, the web browsers of the world today, and you will find a long list of security vulnerabilities attributed to Address Sanitizer. It has proved just stunningly good at finding those specific types of bugs. Okay, so it's called ASAN for short, in case you're wondering. So the code we're going to look at to kind of understand how these bugs work is this little piece of terrible code that I've written. It's using nice, C++ 11 things. We have some constant expressions for hello and world. We have a very silly implementation of hello world here, right? We have routines to copy hello and copy world. They're the same routines, they're just two places, right? Into a buffer, we're going to add a space, and we're going to print it out, all right? But this is going to let me kind of walk you through the different ways in which this code can fail. By the way, throughout the rest of this time, every time I change the code, I would like you to just when you see the bug, put your hand up for a little while, because I kind of want to know when people start spotting the bugs. There's a bug in this code, right? Yeah, and it actually takes a little while to spot the bug in this code. Okay, so let's actually see if we can ask the tools for some help. So at this point, we're going to compile with Clang, and because I'm using lovely new C++ 11. And the way you turn on the sanitizers is, actually first, let's just run the code first. So what happens if we compile this, run it? It works. I thought you guys said there was a bug here. So this is why sanitizers are important. If we didn't have the sanitizers, we couldn't find a lot of bugs that are almost always latent, but not always latent. And you know, the times that they are, helps if I spell the option right and can type. The times that they are latent are never the times when an attacker is trying to leverage them. That's when they're not latent. So now we run it and we get this glorious report. Lots of colors and everything. So the tools work really hard to help you understand what has gone wrong. So we've run this code, and it's put up an error, right? There's a stack buffer overflow. So this is a stack buffer overflow. This is an error that is not typically caught by Valgrind, right? Stack buffer overflow, it says it was a write of size 1 that did it. It goes and it gives you a stack trace and the locations of those of each function here. And actually, hold on. I can make this even prettier. I'm so sorry. I showed you guys the ugly version. It helps if you turn on debug information. Let's try this again. Much better. So it shows you, where everything is. Now we have, right, like nice line file, like file line numbers, right? You can actually click on this in your editor sometimes. It'll jump you to the code, right? And it's going to tell you exactly what this is. My favorite part of this is this line right here. I have never had an easier time tracking down a Stack Overflow than when I've used this tool, because it points an enormous arrow at the variable which I went past. This tool is amazing at helping you actually track down the bug. And I mean, you can see that there's more information here, right? It keeps going to give you more information. It's given you a colorized hex dump of the memory surrounding this overflow. Right? And what this is doing is it's actually showing you all of the metadata attached in the shadow memory, and it's even giving you a legend for how to interpret the colors and the values here, right? So you can actually see that this 03, right? That 03 means that it's partially addressable. Not too surprising, because we only overflowed it by 1 character, right? And so there's only part of this section of memory that's addressable. Not all of it is, and so we realized that there was a bug. All right, make sense? Okay, that's one bug. Let's try changing it up. So, one thing that you might do if you are a casual programmer and just trying to fix this quickly, is you might say well, what if I just do this? I'll just put this on the heap. I don't need to allocate it on the stack. That'll make it better, right? And it turns out that doesn't actually fix any of the bugs here. And if we go and we compile this code again and we run it again, address sanitizer is going to again say, no, you still have bugs all over your code. I mean, now it's saying that this is a heap buffer overflow, right? And it's explaining exactly what's going on, and it's pointing us at the line where we allocated memory in the heap, and it's even giving us the call stack of the allocation, which actually is responsible for allocating this heap memory, rather than the stack frame and the variable, right? Because it understands it has to do different work for different types of vulnerabilities, different types of bugs, to help you diagnose it. All right, so that's pretty nice. But what if I go in and I actually fix this bug? If I give it enough memory, right, I can fix this bug. Anyone spot the bug that I just added to? Maybe a few people? No? Yeah. So now if we run it again, hey, it's bug-free. Turns out that it's not entirely bug-free, but there's a feature that isn't entirely on yet. And I always forget how to turn it on, which is why I have notes. So if we turn on this option to detect leaks, then address sanitizer will actually be able to catch the bug. Because it'll point out that actually I leaked memory here. And it says, I linked memory, right? There's the stack of where it was allocated. Make sense? So far, so good. All right. The reason this isn't on by default is that this is very new. It was added like a couple of months ago, and they're still shaking out some bugs. And the team that does this is really concerned about high quality, and so I'm demoing it a little bit early. This is a very forward-leaning talk. Sorry for that. But it's there. It works most of the time. You just don't really want to turn it on all the time. It has false positives that we haven't finished kind of sorting through and working out. All right. So that caught the leak, which is very nice. But then I might do something just truly terrible, because I might have a lot of other code here, right? And then I eventually will come down and I'll do delete. And then a lot of other code, maybe I call into some other function. And you can see what I've done. I've deleted the buffer a bit early. So that's not going to go well for me. And this is also something that address sanitizer can catch. So if I go and recompile, run it. Address sanitizer says, hey, you have a bug. Sorry for all of the interminable scrolling, but trying to make sure you guys can actually read it. And so this is going to tell me that I have a heap use after free, right? And it shows me where I wrote to that heap memory, right? The exact stack trace. It also tells me all about it, right? It tells me that, like, look, you wrote, 6 bytes inside of this 12-byte region that you allocated. We show you the stack trace of where you deallocated it, which was a bug, right? And where you originally allocated it, so you can actually track down that lifetime that isn't as long as you expected, and hopefully fix your bug. Make sense? All right, but what if it's harder than that? Because that's the easy case, right? I'm not even going to try and reproduce this one. So what if I have a bug that looks a bit like this? I wanted to save you guys the typing. So now I've changed my code a little bit here, all right? Now I'm returning buffers for hello and returning buffers for world. And you can pretty quickly tell that I've got a bug here, right? This is bad code. And fortunately, right, the compiler won't even compile this cleanly, right? It's going to tell you that you've got a bug here right away, because we can do that. But you can imagine that this code might be complex. It might be really subtle in some way that actually defeats this warning and prevents you from doing what you wanted to do here. But even if it did, when you run address sanitize, it's not gonna, But you see, the hard bugs have a special option. There's a reason for the special option. The special option is because this is expensive. What this is doing is it's sequestering every single stack allocation onto a lazily freed thread local pool of stack allocations, so it can track how they're used after your function returns and diagnose what is, in my opinion, the hardest bug to debug in C++ today, which is a use after return. All right, use after return, it tells you that you used it after you returned it, and it points you at the variable that you used after returning. All right, this tool has saved hours and hours of my debugging time every single time I've used it, because every single time I've had a bug that needed this, it was looking like it was going to be days. All right. Okay, so that is address sanitizer. Well, that's fun, but let's try something a little bit more wild and crazy. Let's try thread sanitizer. So I'm not even going to try and write up these bugs for you because this requires some complexity. So first I'm going to walk you through the code. So here I have my version of a bad shared pointer, right? Sean showed you a bad copy on write object. I've got a bad shared pointer. They're actually pretty similar, except that this is the bad shared pointer that I genuinely see more often, because this bad shared pointer is making kind of a classical assumption. It is assuming that these writes and tests, right? And note they're very careful. They capture the result of the decrement because they know that if they don't capture the result of the decrement, the value might change if they read it again. And they've completely bypassed the fact that this is a raw integer. Like, you can't do this. This is a data race. There's no synchronization here. There's no atomicity here. This is just a data race. Unfortunately, this program will work essentially every single time. Well, okay, I've probably made some bugs in my shared pointer implementation because I just threw it together and put it on a slide. But modulo those bugs, this will actually work essentially every single time because it's x86. It's almost, a strong memory model. It almost works. It's close, right? I had to debug one of these things and it failed about once every 200 or 300 billion times it ran. That was challenging, right? It didn't lend itself to your traditional techniques. Fortunately, we have better techniques now. So if I compile this code, and I've got to do a little bit more work to compile this code because it is concurrency, right? Here, let me show you the rest of the code. So for reference, by the way, I love C++ 11 because this is the shortest concurrency bug driver I have ever written. Because I'm able to just spawn up a couple of threads, do some work asynchronously in them, join them at the end. It works beautifully. I love this. So I'm essentially just moving the shared pointer around. I'm not even doing it very many times, okay? That's something really important to note. I'm not even doing it very many times. Worse than that, I've actually got a sleep up here. And this sleep has a decent chance of ending up preventing this race from ever actually occurring in hardware. Well, that does not stop thread sanitizer. So we ask it to sanitize threads. Spelled singularly. We run it, and we get this lovely report. All right. So understanding race conditions is a little bit more complex. So there's more data here. So it says you have a data race, and it's right. It says there was a write of size 4 at a particular address on thread 2. Then it says that there was a prior write of size 4 on thread 1. It gives you the stack traces for these two writes. And if we scroll down, it's also going to give you some extra information. It's going to say, this location is in a particular heap block. This is how much. This is where you allocated that heap block. Essentially trying to tell you where the shared memory, the shared state came from. And it also tells you where these threads were started from. Essentially trying to give you the context you might need to track down exactly how these two threads got a handle to the shared state. The shared state wasn't protected, and they both wrote to it, right? And this helps you track down data races. Would you rather track it down with this? Huh? Hopefully. All right. So then we get to more annoying bugs. So here we have bit fields. All right. Bit fields, I know. I'm sorry, Andre. I had to, though. So here we have some bit fields, right? We have two 8-bit bit fields. They are adjacent bit fields. How many folks realize that that's going to become significant? Ooh, not enough people realize that that's significant. Okay. We have two adjacent bit fields. We create a structure. We initialize them to something. We start up two threads. There's nothing really fancy going on here. Thread A is only looking at field 1. Thread B is only looking at field 2. These two things don't race. They're separate. They're talking to totally separate pieces of memory. Well, unfortunately, C++ disagrees with you. Go back. So if we compile this code, all right, this is going to say, actually, no, there was in fact a race condition here because these writes were of size 2, not of size 1. And the reason is that adjacent bit fields in C++ actually share the same memory location. They do not form distinct memory locations. If you want distinct memory locations, you have to insert some other member or a zero-length bit field in between them in your structure. Until you do that, the compiler is allowed to actually write to all of them. And in fact, with Thread Sanitizer, we cleverly conspire with the compiler to ensure that we do write to all of them so that we can catch exactly this type of potential bug. Right? And we can see that you have the read, you have the write, it forms a race, and it gives you all of the side information you wanted. Make sense? Liking this so far? Learning something about C++ concurrency? Always good. All right, one more TSAN thing. And this one you're going to have to pay attention to. I had to pay attention to it to understand what had happened. Okay, I'm going to walk you through this carefully, because this is going to be hard to follow, okay? We have a class called A. It has a pure virtual function f. This is never implemented. It's pure virtual. This is an abstract class. It has a non-virtual done method, which calls f. Nothing wrong about this, right? Then it acquires a lock. It marks done. It signals a condition variable to wake up other threads, and it prints something out so that you can actually see what's happening here. We have the destructor, which is virtual as it should be. It's an abstract base class here, right? The destructor actually locks the mutex in order to wait for that done method to finish, because we don't want to run the destructor while some other thread is running done. This interface is trying to be reasonably thread safe. And so we wait for that. We wait on the condition variable. Once we hold the exclusive lock, we continue to destroy. That makes some sense? Seem somewhat reasonable, right? We'll wait indefinitely until someone runs done, the first person run done, we then fall through and finish destroying. Question?
Not a question. You told me to raise my hand if I saw the bug.
Ah, okay, wonderful. Some folks are starting to see the bug. Excellent. Do you have a question as who? Excellent. I love it that you're seeing this bug. I didn't see this bug.
Well, you warned us.
So we have mutex, right? We have condition variable, all of these things. I think this is a correct class. Right? And the interesting thing here is at no point do we do any writes to memory in our code without holding an exclusive lock. So this may mean that we have a bug, much like Sean demonstrated how you can have a bug while using atomics, right? But we're not going to have a data race here. At least that's what I thought. Now we have a superclass. We have class B. It derives from A. This class is the dumbest class in the world. It simply provides an empty definition of f and an empty definition of the destructor. There is nothing else going on here. Now in main, we create an object. We give the object the type of the base class. Well, that doesn't particularly matter. We allocate a new one. We then start up a thread. From the thread, we actually run first f, and then we run done. And from a second thread, concurrently, we destroy the object. Now this should be okay, because in the destructor, the first thing we do is block and wait for some other thread to actually call the done method. Now how many people have seen the bug? Few more people have started to spot this bug. This bug terrifies me, by the way. Okay, so what does Thread Sanitizer think about this particular bug? So let's compile it. Run it, and it says there's a data race. Now you remember when I said it was really, really important that you have 0 false positives? The reason for that is so that you can handle this scenario. When you have rooms full of people who stare at you and say, there's not a bug here. And you can actually still convince them, no, there is a bug there, you haven't seen it yet. So let's go up and look for this bug. The bug is a race on the v-pointer inside the virtual class. There is a write outside of a mutex. It's the write to the v-pointer as you enter the base class's destructor, in order to allow the base class's destructor to call virtual functions in its class, not in the derived class. This write to the v-pointer is not atomic. It's not guarded by anything. It's just a race. And if you fix the race by making it atomic, you actually won't fix the bug, because you can have an atomic write and you're still going to have a bug. The bug fundamentally is that there's a race on entering the destructor. right? You cannot enter a base class's virtual destructor in a non-racy way if you believe somehow you're going to synchronize once you're inside of that base class destructor. This is not a viable synchronization pattern. But people do it all the time. Like, you see this in code everywhere. We actually had to change the race detector to specifically not flag as races writes to the base class vPointer when it didn't actually change the vtable it pointed to, because so many people actually hit this bug. It's really, really terrifying. All right, so that's thread sanitizer. Questions about that little crazy bug? Just sadness? There's a lot of sadness about this. Yes?
At a time when you would not change it is when there's nothing added to the virtual function.
That's one instance. The other instance is when there is no derived class. Right?
Then it would be changed.
Well, it turns out that a lot of compilers, because they're allowed to, write the vPointer at the start of the destructor, assuming that someone will eventually derive from it. It's not required. It's a bit of an optimization to remove that, but some compilers don't, and it's legitimate, right? They're allowed to do that, but it triggers a race. All right, so just a couple more demos, and then I will be done. Oh, you fix this by not synchronizing inside of a base class destructor, right? Like, synchronize outside of that. You have to pop out a level and synchronize first and then destroy the object.
So in the derived class object destructor, which always is called a base class destructor, you put the synchronization where? Because didn't that happen before that?
So the question that we're kind of digging in here is how could you fix this? And what I'm trying to convey is that there's not actually a direct fix for this. There may be a clever one that I haven't thought of, but the way I typically tell people to fix this is to take this synchronization we have at the start of the destructor and to take it out of the destructor entirely and to put it in some other method, which is essentially to, coalesce or become ready to be destroyed. And only after that synchronization has taken place do you start the destructor calls, right? You don't want to use delete as the instigator for a synchronized destruction of an object, right? That's just guidance. Maybe there's a way to do it safely, but I wouldn't. That seems too clever for my taste. All right, really quickly, let's just go through a couple more demos. I don't have too many more here. So I want to demo msan very briefly, but I want to mention this is easily the most forward-leaning of all the demos I'm showing you, because msan is just frighteningly hard to use currently. And it works about the way you'd expect, right? You have some variable you don't initialize. Did folks see that? You have a variable, you don't initialize it, right? You branch on it, you return. This is total undefined behavior, right? Your program may explode in fireworks and a shower of debris. Fortunately, we can detect it. Oh. Now, when we detect this, though, there's kind of some unfortunate consequences that are the reality of msan, and part of why it's still a much less mature tool. When we run this and we detect it, we're not going to give you any really nice information. You remember all the beautiful, colorful reports we've been looking at? This one's kind of underwhelming, right? All we say is that, like, yes, you use an uninitialized variable. It turns out that msan is really, really resource intensive. Like, really resource intensive. It is the slowest of all of these tools. And the way we keep it fast is by doing very little. It keeps a very small amount of state around in order to stay fast. This lets it actually run at a reasonable speed. But if you need to debug it, you actually pass another flag. I may have forgotten how to spell. Not today. Excellent. You can pass another flag and it'll track all of the extra state necessary to produce one more line, but it's the most important line I've ever gotten from a dynamic analysis tool looking for uninitialized memory. It's the name of the variable. Valgrind does not produce this. It actually can't. It's really, really hard. Like, I say Valgrind can't do this. I'm actually not knocking Valgrind. Valgrind's an amazing dynamic analysis tool that's based on binary instrumentation. Binary instrumentation makes doing this next to impossible. Doing it in the compiler allows us to stash away information during the compilation. Right, the option wasn't when I ran the binary. It's when I built the binary. We have to stash away extra instrumentation in the binary in order to get there. Anyways, so we have X. That helps you debug it. makes things go faster. All right, let's do one more demo. And I will be out of here. Okay, so this is UBSAN. I actually have a bunch of demos here, but I'm just going to keep it simple for now. So let's look at one of these demos. Right, pretty straightforward demo, right? Integer overflow, nothing too fancy here. But we can actually catch this at compile time. By asking it to sanitize our behavior. I know it's kind of strange. Have they misspelled it?
Are they British?
They may, well, yes, actually, the person who implemented this is British, but I don't think he spelled it that way. Anyways, I don't want to spend too much time on this. So the one thing I did want to show you is the last bug that this will catch. Because this one's kind of hard. So this one is actually round tripping the largest integer value through a floating point value. And the representation you get back out here is totally undefined. But there's not like a lot of clear reasons why, and there's not a lot of tools that will catch this. And it's really, really nice that undefined, the UBSAN actually will catch this for you. Okay. So with that, if we can go back to the presentation really quickly, I will sum up. Get us out of here. So complexity is what I feel is kind of the biggest challenge we face, and fortunately I believe that tools can help. So remember why we use tools. We want to automate manual tasks, right? We want to accelerate the complex tasks, and we want to find the bugs faster and use some dynamic analysis to track down the long tail of subtle and complex bugs. Hopefully, you're going to combine all of this with really rigorous testing of your software, and that's how we keep bugs from going into it. Now, my hope is that if you use all these tools and you develop code somewhat like I'm showing you here, you can write correct, reliable C++, and it's going to be fun, it's going to be easy, it's not going to be this burning dragon. So, with that, I also want to mention a huge thanks to all of the LLVM hackers out there that have helped. I just presented essentially none of my own work. All right, this is mostly done by other people, and they deserve all of the credit. All right, they've done a tremendous job building all of these tools. But there is one more thing I think I want to talk about, if Herb will give me time.
I love this plan. I'm excited to be a part of it. Let's do it.
So if we can switch over to a different computer briefly. Hopefully it will work. Live demo. Hopefully we can switch. Excellent. This may be a little bit of a surprise for people because this is a Windows computer, and I'm going to load up Visual Studio 2012, and I am going to open a project. So this is C++ code on Windows, and you can look around. There's plenty of your standard C++ code on Windows. Nothing too surprising going on here. But what's really amazing is that if I look at this code, so this code looks really ugly to me. I don't work on Windows, I'm sorry. It's probably beautiful in other people's eyes. I can highlight this code, and I can run a little command which will format it for me by running clang format. Because clang format works in Visual Studio just fine. And I can even do something kind of strange. So I can do something really strange, and if I really care, I can actually go in. So I can go in and configure clang format to make it print stuff well. But there's something else that I think is actually a little bit more relevant as I figure out how to undo my damage. You can tell how often I do this. So the other thing I want to do is, it turns out that there's a bug in this code. And if we were to build it, right, we could actually see that bug. So I think we should build it real quick. But there's something strange you're going to see when we build it, and that's caret diagnostics. Because we're building this with Clang on Windows. Now this is a DirectX Windows application written in C++, being compiled with Clang, being linked with the Windows DirectX libraries, and running on Windows. Unfortunately, it doesn't run correctly. But wait. I know how to fix this. If I go back to my IDE, I can move from debug to ASAN. And if I build it again, I may get a little bit more information about what's going wrong with my program. Where did it go?
Output.
Come on.
Output.
So I also can't see the mouse. So here you can see that, we actually have ASAN running in Windows, catching a stack use after return, the hard bug to catch.
Nice.
So we've been working really, really hard. If we can go back to the slides quickly, we've been working really, really hard to actually bring LVM and Clang and all the technologies we're building to Windows. And if you go to this website right now, you can bring down their server, but in the process, you can also grab installers for LVM and Clang and for the Visual Studio plugin, which lets you, have Clang format by mashing a key. You can install them and you can use them with Visual Studio 2012 today. So that's live. Now these are alpha quality tools. I can't say that enough. Like we built this, I think, this morning. I am certain it contains bugs, okay? And the other thing is that we're not done here, right? So we've started this process, but this is a long road, okay? We don't support a lot of C++ on Windows. If you use IO streams, bad things happen right now, okay? If you use exceptions or RTTI or all kinds of features, like we're not done. But we're working on it, progress is starting to happen, and Scott, you actually have a compiler you can download and install. So with that, thank you very much.
Thank you. So.